Hey, what's up, guys? Okay, so in this video, that we are going to prove that something very deep called the Szemerédi regularity lemma, and the proof looks not so simple, but yeah, it looks very very non-trivial, and the proof strategy is very interesting, and so this theorem is very deep and has so many applications. Okay, so I will first give a statement and give the proof, and hope you guys subscribe to my channel. Okay, and yeah, so yeah, let me just give a definition. Okay, so we are talking about graph theory, right? So let's say so first we need to define an idea called edge density. So idea is that all the setting start from some graph G, simple graph G, and we can define the edge density. So if I take the two subset of graph G subsets of the vertices, yeah, so these are two subsets. Okay, then I can define the edge density, usually called dxy, to be the number of edges from x to y. So not divided by x and y. Okay, so e of xy is basically the number of edges. So basically, let's say, so it's the uv in e such that right, so this edge, right, such that u belongs to x and v belongs to y. Okay, so this set basically, let's say this is x, this is y, and you have, let's say, u and v, and you just count how number of pair. Okay, you just count number of pair which counted. So this is the edge density. You count number of it and divide it by x and y. Okay, so this is called edge density. Okay, and now you can give a definition too, called the epsilon regular pair. Okay, so let's say given epsilon, let's say you pick epsilon greater than 0, and so we say x and y are epsilon regular if what? If, let's say, for any subset A and B. So if you take A, let me just for any subset A subset of X and the B is a subset of Y, and satisfied. So these are conditions. So these are like for every subset, A belongs to subset of X and the B subset of Y satisfied. If A is large enough, basically means that A is at least epsilon fraction of X and B is at least epsilon fraction of Y. Right, so you take two subsets, right? And such that the edge density between A and B minus the edge density between X and Y, they are close enough, right? So close enough, basically less than epsilon. Okay, so this is the epsilon regular, right? So this means it is X, it is our Y, right? If you take only A and B, were large enough, let's say this is A and B, and if A and B are large enough, mean that they basically have at least the epsilon fraction, then you want to say that this density is similar as the total density, and they are close enough, right? So yeah, so imagine that you start from X and Y and you pick A randomly and B randomly, and you will say that this should capture the idea why this is called epsilon regular. Okay, so hopefully definition are clear. Start from X and Y, epsilon regular if their subset, if base two subsets are large enough, the density are close enough. Okay, so now you can start with definition 3 called the epsilon. This is called epsilon called regular partition. Okay, so if I partition my V, so partition, I say I partition. Partition basically means that I separate V into the V1 up to, let's say, VK part. So usually this is called partition. Basically, there are disjoint union equals to the whole set V. Okay, so basically it's meant that your Vi equals to V. So each vertex will belongs to one part, and each part are disjoint. Okay. It's called epsilon regular partition. partition. If you sum over the vi vj, let's say ij is irregular. So you can count the number of pair. Sorry, vi vj are irregular. So if you count the number of irregular pair, right? So remember previous I defined the epsilon regular. So now you can you can define a vi vj called epsilon irregular, by means they're not epsilon regular. So you count the number of irregular pair, vi vj, epsilon irregular pair, and you sum over the size of it, right? So it should be less enough. It should not be so large. So it should be less than the number of vertices squared. Epsilon times the number of vertices squared. Okay. So this is the sum over the, so basically this just say a sum over the sides of epsilon irregular pair is small enough. Okay, so now we have three definitions, right? So one is called the energy density, which is simple, and then we have the epsilon regular pair, and we define the epsilon regular partition by summing all the irregular pair. Okay, so let me just write down the Szemerédi. So Szemerédi regularity. Okay, so this Szemerédi regularity lemma says the following: says that for every epsilon greater than 0, there exists m. Okay, so this m is only the dependent on epsilon, right? So and then for all every, so these are condition. Then so these are condition. Okay. And for every graph G, so for every graph, so for for all graph G V, there is a epsilon regular partition of G into at most n parts. Okay, so what this theorem is deep. It's very deep because that first you're talking about for all graph G, right? Or you can say maybe the large enough graph G. But what this theorem says that there's always an epsilon regular partition. So you can always find the epsilon regular partition into at most n parts. And m is only depend on epsilon. It's not depend on the graph size. Not depends on size of graph. So so obviously that if you partition your graph, right? If you partition your graph into like each vertices belongs to its own parts. Right? So G has n vertices, there you partition into n parts, then obviously basically it's epsilon regular, right? Because they're always like there's only two vertices. There's for each part there's only one vertices. But the deep of this is basically say that you can always the size of V can be arbitrarily large. The size of graph can be arbitrarily large. Arbitrary can be as 2 to the, let's say 1 of epsilon, or 1 of epsilon, or 1 of epsilon, can keep growing, can be astronomically large. But this m of epsilon can only depends on epsilon. So whenever your graph is arbitrarily large, you can always at least you can always partition your G into all these small parts, and they are basically finite. Only depends on epsilon. Okay, so you can like spend some time to think why this is, how deep is this theorem is. But if you start this, this theorem can prove many like astonishing results. Okay, so this is the lemma. Okay, so in order to do the proof is much more complicated. Okay, so okay, let me just give a statement, and maybe another video give the proof. So the idea, let me just say the idea, right? So the idea is that your idea is that you want to say something. Okay, so you first define an idea called energy. Okay, so basically given a partition. So if you start with some partition of G, then you define a quantity called energy. This energy is a function of partition. Okay. And then you start, so you can start with trivial partition. And the second one is you claim you claim that if the partition P is not epsilon regular, then you just define a way to just keep partition. Okay, you just keep partition. You just take the each part, each small parts and do the partition again. Okay, do the partition again, and you just keep going. Okay, and you want to claim, and the idea is that this quantity energy, let's say this is Q. Okay, so this energy Q is always bounded by from 0 to 1. Okay, and you want to say that if this partition is not epsilon regular, and then you do the partition again, okay, then energy will increase. Okay, so energy will increase by some function of epsilon. Okay, is non-zero. Okay, let's say the epsilon to some power c. Okay, so basically each time you repartition, you get some, and your energy will increase by epsilon to a c. Okay, so but basically this means that the second step, right? Second step cannot forever, right? You cannot keep doing, right? Because your energy start from 0, and every time you do is epsilon irregular, you always increase your epsilon by epsilon c amount. Okay, and so it will terminate. Okay, and so once it terminates, then you can use the second step to say that you can bound the number of parts by a function of epsilon by this guy. Okay, so the idea is that you can define some energy Q where you start with maybe some number, and every time you do the repartition, if it's epsilon not regular, epsilon irregular, then you do the energy will increase. And if it's still not epsilon regular, then you keep increase. But there is a 1 here, right? So basically up to some step, this repartition will terminate. Okay, and then you can show that since it terminates, so that point must be epsilon regular. So this point must be epsilon regular partition. Okay, so yeah, this is the statement, and maybe in the next video that I will give the proof.